So what we're going to do today are Riemann sums. Everything in math either is exactly what it sounds like or it's named after the guy that came up with it. What does the word sum mean? Addition. So you're going to add stuff together. So we're going to consider the function x squared. We're just going to start with something really basic. It's a parabola, but we're only looking at it from 0 to 1. So do you see how we're looking at this very tiny piece of the parabola? I have this all graphed on here for you so you don't have to draw anything. All right, you're together? All right. Now, what we're trying to estimate, and if we're estimating, are we finding it exactly? No, it's estimation of the area underneath here. The reason that you can't just do like a triangle is it's curved. Do you see what I'm saying there? So we're estimating an area for this curved shape. And to do that, we're going to use rectangles. And we have split this interval into how many sub-intervals? We call them sub-intervals. How many do we have here? It's a little tricky for this first. Actually, 4, it's just the first one didn't end up giving us a rectangle, but we're going to find the areas of those rectangles and use that to estimate the area under the curve. So what I like to do is highlight the heights of the rectangles. I just feel like highlighting helps that. And for the first one, because it's sort of non-existent, I just put a dot there. We're going to pretend there's a rectangle there. It just has a height of what? 0. It has a height of nothing. Okay. So this is what is called a left Riemann sum. And why do you think it would be a left sum versus, right? Left side. It's the left side of each of the sub-intervals that we're using to get our heights. Do you see that there? If you are left and right challenged, this might be hard. I am sometimes directionally challenged too. Remember, it's the one that makes the L. Okay. So do you see how we're using the left side of the sub-intervals? Okay. Now, this is from 0 to 1, and we split it into 4 uniform, meaning all the same sub-intervals. What's the length of each one of these sub-intervals? Yeah, and now I like fractions. We're going to go with fractions, so it would be 1/4. Okay. Now, these are decimals on here. I don't really like that. I'm going to say this is 1/4, and this is 1/2, and this is 3/4, and then this is 1. You're going to see why I did that in a second. Because to get the heights of your rectangles, you need to plug those numbers into the function. And this one's 0 here. And what was our function? X squared. So we're going to plug each of those into x squared. Here we go. 0 squared. 0. 1/4 squared. 1/16. Do you see why fractions are better than decimals? Like, bring you over to my side here. 1/2 squared. 1/4, because 2 squared is 4. 3/4 squared. 9/16. 3. You just square the numerator and square the denominator. 3 squared is 9. 4 squared is 16. All right, so we're going to do our rectangles. How do you get the area of a rectangle? Yeah, length times width, or base times height. One dimension times the other. So for this first one, the base is 1/4, and the height is nothing. Write it, though, and you'll see why, because this is very much a pattern thing, and that's part of the pattern. All right, plus, now we're going to do this rectangle. What's the base? This length right here that I'm pointing at. 1/4. And what's the height of that rectangle? We highlighted it. 1/16. Good job. All right, next one. This rectangle right here, the one I'm coloring in. What is the base of it? 1/4. Not trying to trick you. And then the height is what? Oh, so that one's actually a square. All right, and then the last one, this one right here. What is the base? 1/4. And the height is 9/16. Now, hopefully at that point you were like, what do you notice each one of them has? Now, this only works if the sub-intervals are uniform, meaning they're all the same. If they're all different amounts, you can't get away with this. But what we're going to do is factor a 1/4 out of that, and you would be left with 0 plus 1/16 plus 1/4 plus 9/16. And that's the sort of abbreviated way. I do still recommend writing the 0, and this is why. It said we have 4 sub-intervals. That means you should have 4 numbers in your sum. Do you see how there are 4 numbers added together? Those should match. The number of sub-intervals and the number of things, items in your sum, terms in your sum is what you should have. Now, for the sake of time, I'm going to tell you what that comes out to as a decimal. It is 0.21875. I have these all written down, so I'm going to just look off my paper and tell you. Did you trust me? Okay, just typed it in the calculator. Is this an underestimate or an overestimate of the true area under this graph that we are trying to find? Yeah, do you see how we're missing like all of these gaps? So your left sum is an underestimate if your function is increasing. Do you see why? If the function is going up and you take the left side of it, do you see how that's the lower down side? Okay. Now, it would be an overestimate if your function was doing what? And let me humor me for 1 second while I show this to you. All right. This was me writing scribbles to get the pens to work. Ignore that. Do you see how if you had a function that was decreasing? If you take the left side, and I found it helps if you write an L and an R. Do you see how the left side is higher up than the right side? So that would be an overestimate. Okay. So what we just did was the left Riemann sum. This one is going to be a right Riemann sum. And this is, again, where I think the highlighting really helps so that you can see the difference, because this is going to be largely the same problem because I'm not changing the graph. This is still the graph of x squared. It's still this little piece of the parabola from 0 to 1. Our sub-intervals still have a length of what? What is each sub-interval still? Because I didn't change it. Yeah, they're all still a quarter. They're all still 1/4. Okay. It's just this time when you highlight, the way that you get the heights of your rectangles is that you're using the right side of the sub-interval. And so again, the way that you get the heights is you plug into the function. It's f of whatever that number is. So you just plug these in to get the heights because it's where it hits the graph. Again, we already found them above. This one's 1/16. And if you don't want to write them again, I guess you don't have to. I like to have them there. It doesn't take that long. And then this is the one new one. We didn't have that one before, but it's just going to be 1. 1 squared is 1. So it's just going to end up being 1. So I'm going to skip this version of it and jump straight to the abbreviated version. And again, you can only get away with this when your sub-intervals are all uniform. If they're all different lengths, then you can't get away with that. But these are all 1/4. All the bases are 1/4. And then you're going to add up your heights. So 1/16 plus 1/4 plus 9/16 plus 1. And again, even if one of them ends up being 0, I recommend keeping it in there because if it says 4 sub-intervals, you should have 4 numbers added together. And then it's a way you can check like, oh, did I get them all? For the sake of time, instead of me, typing this into a calculator for you, I'm going to go ahead and tell you that the decimal is 0.46875. Just so that you have that there. That's what that comes out to in case you're interested. And is it an underestimate or an overestimate of the actual area? And yeah, definitely over. Do you see how all this part is like extra that's hanging over the graph? So this is going to be an overestimate if your function is increasing. Our function is increasing. So if we take the right side of it, that's higher up. And it would be an underestimate if your function is decreasing. And if you'll humor me for a second, I'm going to grab a sticky note and just draw you a little picture. Should have said everything I wanted to say there. If you draw a decreasing graph, and it doesn't need to be fancy, look, this is decreasing. If you pull from the right side of it, do you see how the right side is lower down? It's going to be an underestimate. When I'm thinking about and that's why I love this topic so much. It's so visual. Like you can just draw a decreasing line and go, oh, the left side's going to be over, the right side's going to be under. Like you can see it. It's very concrete. So I like this topic. All right, go ahead and flip to the next one. We just did left and right. And I want you to look at the graph because I drew all these graphs on here for you and we're going to highlight. What do you think this one is? It's the middle. It's called a midpoint sum. So if you want to highlight, you're getting your heights of your rectangles from the center of your subinterval. So this one's a midpoint sum. Now this does throw people off sometimes because you're pulling from the center of the subinterval, but the lengths of each subinterval still did not change. Do you see how the base of each of these rectangles is still 1/4? Like I'm not changing that. So it's going to be 1/4, and then we're going to have our sum in here, and we should have 4 numbers added together. Now here's where we have to actually do like some math. Is we have to figure out what those values are. You plug into the function, which is still x squared, but I need to figure out what these values are. And I like fractions. I think they're a whole lot easier to deal with than decimals. What is halfway between 0 and 1/4? 1/8. This reminds me of baking, like if you need to like have a recipe or something like that. So after you get that, you can kind of just count by eighths. Look, that's 1/8. 1/4 is 2/8. So the next one is, yeah, good, 3/8. 1/2 is 4/8. So this one's 5/8. Are you coming with me on this? Here, okay. And then when you plug them into the function, again, the function is just x squared. You're just going to take each of those numbers and square them. So 1/8 squared is 1/64. What would be 3/8 squared? Yep, 9/64. Good. And then this one would be 25/64. And yep. And actually, I wrote them there so you could see like those are the heights, but I'm just going to recopy those numbers and add them together in here. So again, if there's 4 subintervals, you should have 4 numbers added together in your sum. And just so that you have it, this comes out to 0.328125, if you are interested in the decimal. Now this one's really hard to tell if it's over or under. So I'm going to tell you how you come up with it. It's an underestimate if your function is concave up. Don't think about it too hard. I've actually never seen that come up in a question. I'm just telling you because it's true and I like to be thorough. And it'll be an overestimate if your function is concave down. So let's think about what this one would be. Is your graph of x squared concave up or concave down? Yeah, concave up. So that means this would be an underestimate. But do you think this one's a better estimate of like the true area than the left or the right ones? Yeah, because do you see how there's like a little bit that's hanging over, but then there's a little bit that's under, like they're going to balance out. Still not perfect. It's still an estimate, but it's a better estimate than the other ones that we did. All right, and then the last type of sum is a trapezoidal sum. So instead of rectangles, you're going to use trapezoids. Do you all know what a trapezoid is? 2 sides are parallel. The other 2 aren't. Okay. You do need to know, actually, I'll use my highlighter for this. You do need to know the area formula for a trapezoid. That's one that you have to have memorized. It's 1/2 the height, and then you add the bases together. Here's the thing. They're all on their sides. Like, here, look, just watch for a second and I'll show you. All your trapezoids are on their sides. So do you see how these are the heights? Do you get what I'm saying there? So what is the height of every single trapezoid? 1/4. It's, you know, the length of your subinterval. Do you see how this is a trapezoid? Do you see it? I can't like walk up to you and shake you and be like, do you see it? But do you see it's a trapezoid? 4 of them? Okay, cool. So let's go ahead and highlight. And we're going to write this out the long way, and then I'll show you the abbreviated way. And again, you can only do the abbreviated way if your subintervals are what? The same, uniform, all the same. If they're all different, then you can't get away with shortening it, okay? So we've done this on all the other ones. I'm just going to write these out one more time just so that we have them. What was that? 1/16, 1/4, 9/16, and 1. We did those on the other problems. I'm just writing them out again so that we've got them there. So we're going to have 4 trapezoids all added together. As a heads up, it's going to get long. You're not going to fit it all on one line. You're going to have to go down to the next, or well, I mean, I guess you can. It'll go into your graph. Just as a heads up, start all the way over here on the side. So you start with a 1/2 simply because the formula has a 1/2 in it. Like that's just there. And then what did we just say the height of every single one of these trapezoids is? Yeah, 1/4. It's the length of the subinterval. They're all on their sides. So these are the heights. So 1/4. And then you add the bases together. So watch me point to this. This is your first trapezoid. So your bases are 0 and 1/16. So it's going to be 0 plus 1/16. So it's actually not a trapezoid. It's a what? What shape did we get for our first one? It's actually a triangle. A triangle, I guess, is a form of trapezoid where one of the bases is nothing. Okay. Buckle up. We're going to do that 3 more times. So 1/2 times 1/4. Good. And then look at the second one here. I'll cover up everything except that second trapezoid. Do you see how it's the 1/16 and the 1/4? Okay. Halfway there. It's not hard. It's just a little bit tedious is all. All right. 1/2 times what? 1/4. And then look just at the third one. What are you going to add together? 1/4 and 9/16. And then last one, I think I might be able to make this fit here. 1/2 times 1/4. And then what would you add together for the last one? And 1. Perfect. So if you want to write that the abbreviated way and not have it be super long, what do all 4 of these share in common? What have they all got? So they're basically going to factor it out. Yeah, 1/2, because it's in the formula, you can't escape that 1/2. And then it would be the length of the subinterval. And now watch me point to this. Do you see how the 0 and the 1 are only in there once? But do you see how the 1/16 is in there twice? And then the 1/4 is in there twice, and the 9/16 is in there twice? That's because those are shared in between each of these. But the 0 and the 1 are the ones on the end. So those are only there once. Do you get what I'm saying? So here is how you do it the abbreviated way. You would have the 0 just once and write it because it's part of the pattern. And then you would have the 1/16, but there's 2 of them. And then you would have the 1/4, but there's 2 of them. And you would have the 9/16, but there's 2 of them. And then you only have the 1 once. So again, the ones in the middle get shared, so they get doubled. The ones on the end only get used once. Is this making sense? Okay. And if you were interested, that as a decimal is, and I have a reason why I'm telling you all these decimals. Because you get that these are all estimates, right? They're not the actual answer. We're estimating. So that when I give you the actual answer, you can like compare them. Like that's why I'm doing, I have a reason. Okay. Now over, or does anyone want to give it a guess? Do you think this is slightly over or slightly under? It's a pretty good estimation, but what do you think? Slightly over, and it's because of the concavity of the graph. This is going to be over if your function is concave up, and it's going to be under if your graph is concave down. Now, I don't necessarily straight up memorize that. I'm a bad memorizer, but I'm a very visual person and I like a picture. So here's what I do, if you will humor me for a second. If you draw something that's concave up, just watch. Do you see how your trapezoids will be very slightly over it? You see what I'm saying? All right. And here's something concave down. Do you see how if you draw in trapezoids, they're very slightly underneath? Like you can always just draw a picture. And then the way I remember the midpoint one is they're opposites of each other. Do you see that? This one's under if concave up. This one's over if concave up. That's how I remember them, is I figure out this one and then midpoint is just the opposite of that. Now, we don't necessarily need to really write a whole lot for either of these. It's supposed to be a conversational thing. So let's see what I get out of you. What do you think is the best estimate or the worst estimate? What are your thoughts? We're just going to talk about it. You think this one's best? Why do you think it's better than this one? There's not a right or wrong answer. We're just talking. Yeah, like you can see a very tiny gap here. Does anyone think this one's better? I feel like this one is, I feel like this one's always going to be pretty accurate, like consistently. I feel like midpoint is, depending on what your graph looked like, that could be really wrong, depending. So I think I would have to agree with you. I think the trapezoidal one is probably the best one. What could you change about these to make them more accurate? Like say you were forced to do one of these ones. Say you were forced to do a right sum. How could you make it better? Like how could you make this not be so much extra over here? More, and we don't call them section. You're correct. It's the right answer, but we call them sub intervals. Thank you. More sub intervals. The more, the better. Because if you have more of them and they get narrower and narrower and narrower, do you get that error is going to be less and less? You'll have less error. Okay, so to make it more accurate, more sub intervals. Cool. We'll do a couple more and then I'm going to give you too long of a brain break because I want you to be able to, only 40 minutes left. Might not do a break today. All right, so we're going to find each of these for this function. Actually, you know what? I'm going to skip that one because we're going to do the exact same thing here. For the sake of time, I'm going to skip that one. We're going to just jump down to number 8. So we're going to use the 4 subintervals indicated in the table to do a left Riemann sum. I strongly recommend that you circle them. This is the first one. This is the second one. This is the third one. And this is the fourth one. And so we should have 4 rectangles all added up. Here's the $1 million question. Are your subintervals all uniform? Are they all the same? No. Why not? Yeah, like do you see how it's 3, 8, 10, 16? It's not counting by the same amount every time. So you can't write this the abbreviated way. You're going to have to actually write out all 4 rectangles. Okay, what is the length of the first subinterval? 3. 0 to 3 is a length of 3. Do you see that? All right, so 3 times what? Well, it says left sum. Don't overthink this. Which number is on the left, 10 or 12.5? 10. Plus, now we're going to do the next one, the 3 to 8. What's the length of that subinterval? How'd you get 5? Because you're all geniuses and that's correct. 8 minus 3, the difference between them. All right. Now, if you're looking at that, which is the number on the left? 12.5. Halfway there. What's the next one? 2. Good. From 8 to 10 is a length of 2 times 17.5. And then the last one, 6 times, and for the love of my sanity, you should do what with that? Leave it, nothing at all. This shows up on the AP exam every single year. It's usually worth 2 points, and you just want to be like, ka-ching, 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 points, points, points. You will get it. It's super easy. Leave it alone. Now, I think there's something else there. Underestimate or overestimate, justify your answer. All right, look at these numbers, 10, 12, 17, 28, 46. What are they doing? Increasing. Just go like this. It doesn't need to be fancy. Increasing. And which sum did we do, left or right? Is the left side higher up or lower down? Do you see how it's lower on the left side? Okay, so we're going to say underestimate because f of x is increasing and this is a left sum. I would hope they would take that, for heaven's sake. All right, use the 4 subintervals to do a trapezoidal sum. You can't abbreviate it because all the subintervals are different. Let's see without flipping over who remembers what fraction is in the formula. Like it's just there. Good, 1/2, right kind of small. This is gonna get lengthy. 1/2, all right, what's the length of your first subinterval? 3. And then you add the bases together. So 10 plus 12.5. And then you just do that 3 more times. Like just do it again. Plus 1/2 times what? What's the length of the next one? 5, good. And then 12.5 plus 17.5. I'm going to come down to the next line. So I'm going to run out of space. Plus 1/2, like just literally just do it again. 1/2 times 2, good. And then 17.5 plus 28. And then last one, I'm not going to say this out loud anymore because I'm sure that that's getting annoying. You guys try it and then just make sure yours matches mine. And you do nothing to that, nothing at all. Now here's the big idea of what we were headed towards. Everything we've done so far are estimates. They are not the true answer. What is a definite integral is the actual area under the graph. Like the true perfect answer. It's not an estimate. It's like perfect, like the answer. And so we said we'd get a better estimate if we had more subintervals. What it means is that your subintervals approach, what do you think? If more is better, they have to approach infinity. Does that feel like a limit? Because it should. All right. You want your limit as your subintervals approach infinity. And here's how we write it. And you're going to get used to this symbol. It looks like this. It's like a symbol on a violin. Or do you have a sibling that's taking calculus or a friend that's taking calculus? You see them write this. It's called an integral symbol is what that is. From A to B, so from a starting point to an ending point of your function, and then we put dx at the end. Here's what that all means. When we plugged into the function, that gave us the height of our rectangles. dx is the change in x. Has anyone taken physics or chemistry where you use a delta? Do you know the little triangle, delta x? That's what that is. That's the length of your subintervals. That's the base of your rectangles. So it's base times height, and the integral means add it all up. It's a sum. You add them all up. So what I want us to try and do is write an integral for that very first problem we did. So flip back to the front page, or actually just flip over because we've got it here too. We're going from where to where? 0 to 1. Do you see that there? 0 to 1, so it would look like this. 0 to 1. What was the function? X squared, and then you put a dx at the end. That's it. Now let me make sure I'm on my calculator. I'm going to share my screen so that this will show up on the video. You guys are about to love this. Can you watch? All right, I'm going to share. Here's our calculator. If you type int, an integral will appear. int, do you see how I did that there? From 0 to 1. Now you do need parentheses. It's x squared dx. Oh, what is the actual true area? Not an estimate, but like the perfect area. 1/3. 0.3333333. The actual area of this is 1/3. Perfectly. So do you see how this is slightly below? This is slightly above. Cool, right? Kind of geeks me out that you can find an area of something like that. You couldn't do it until now. You need calculus to do it. You can find areas of all kinds of wonky shapes, like this one. We're just going to practice setting it up for right now. It'll be integral from where to where. I'm just trying to get you used to the notation. So from where to where for this 1 to 5 is it. Leave a gap and put a dx at the end. And we need to write a function for that parabola. This is kind of like welcome back to algebra 2 / pre-calculus. How would you write that graph? It's a parabola. So what do you think? You have to find where the center is using words like up, down, left, right. Good, it went right 3, up 4. So it'll be x minus 3. There will be a plus 4, but what else do I need? Squared, and I actually need one more thing. Good. Y a negative. It's upside down. That's it. If I were to type that into Desmos, it would give me the area of that. Cool, right? Let's try this one. Integral from where to where? It's written on there super tiny. You can see it. Although you all passed pre-calc, so you should actually know what those are anyway. Good. Negative pi over 2 to pi over 2. What's that a graph of? Why is it cosine? Because it starts at 1. This one I am going to type in so that you can see it. Because this one geeks me out too. This is where I start to get excited. I'm like, oh, this is fun. All right, so we're going to go from negative pi. Oh, the way you can type pi in here is pi. So negative pi over 2 to positive pi over 2. And again, you need these parentheses here. Radians is the default, so just don't change it. Cosine x dx. 2. This area is 2. No one else thinks that's neat? That's so neat. If this is 2, what does that mean each one of these little bumps is worth? 1. Isn't that cool? Like, it just is. Like, I didn't make it be that. Like, so neat. So neat. Cool. You can disagree, but I'm right. So cool. Yeah. Yeah, all I'm asking you to do is set them up. I'm just trying to get you used to the notation right now. We're going to do that next time. Right now, all I want you to do is get used to writing the symbols is it. Now, this one is going to take 2 integrals. You're going to need one for this little part and then one for this part because it's piecewise. It got broken. So let's do the first one. Again, just trying to get you used to the notation. It would be from where to where for this first little bit. -1 to 0. Remember, it involves the x-axis. Okay, -1 to 0. Leave a little gap, dx. We'll come back to that. Plus, and then do another integral. What are going to be the boundaries on that one? From where to where? Yeah, 0 to 2, leave a gap and put a dx. Now we have to write the, can I skip that part for the sake of time? Could you write those functions and stick them in there? Do you get what I'm saying? Like that one's a line, that one's a parabola that's upside down. You would need a negative. Okay, cool. This one, do you see how there is a discontinuity, right? Oh, removable or non-removable? Removable, good job. Now we want to go from -2 to 3. So we want this, but you have to break it where the discontinuity happens. Okay, it's like a technicality. So it would be from where to where for the first one. We're gonna have to do the same thing and put 2 separate integrals. So -2 to 2. Here, let's write this one. What is the slope looks like -1, down 1 over 1. So -x plus 3 dx. Plus, and then what are the boundaries on the other one? Yep, 2 to 3, and then it's the same function. So just copy it again. The dx at the end is really important. That's the length of the subinterval, remember? Now this last part, I put this on here. I copy and pasted it from the from College Board, good old College Board. You can read that if you want. I'm going to just show you how to hoop jump through this is basically what we're doing. Now, I do want you to have an understanding of it, though. Do you see how its limit n goes to infinity? That's because we want infinite subintervals. Are you with me there? And does anyone know what this Greek letter is? It's a part of y'all's vernacular now. It's like become a thing. Sigma, thank you. I really hate that that's been like stolen from us mathematicians. But anyway, what it means is add it all together, adding up all of the rectangles. So you want an infinite number of rectangles and you want to add them all together. That's all that means. Okay, that's all that means. So we are going to draw our integral symbol. And your boundaries will be 2 to 7. Let me explain to you how I grabbed those numbers from there. Do you see this part right here that's in the parentheses? That part represents x. I'm going to get to that in a second when I write it over here. But do you see how it starts at 2? It's 2 plus something. So your lower boundary is 2. Why do you think the upper one is 7 if you had to guess? Do you see how the delta is 5? This 5 is your dx or your delta x. So 2 plus 5 is 7. The math I did there is 2 plus 5 equals 7. That's all that is. Okay. And then what goes in there is ln of x and then dx. Do you see how it was ln of stuff? Like ln of x? Let's just try it again. It's a whole bunch of symbols, but that's all that it means. It means you want to add up an infinite number of rectangles. Where do you think this one's going to start? This is your x here. So it starts at -2 to 1. Good job. How'd you get 1? Plus 3. Good. And do you see how it's 2 times all of this? So it's 2x dx. The function is usually not all that complicated. Now I threw this one on here because I saw one like it on AP Classroom. Do you see how all these other ones, these fives match and these threes match, and then these ones don't match? Well, they have to. So you can't keep that 3 in there. You have to just have this part be x so that it's a 1k in front of there. So you want to think of this as nothing plus 1k over n. Do you see what I'm saying? Like you can only use that part of it because the ones have to match. So what would your lower boundary be then? Where would it have to start at? 0 to 1, and then your function is square root of 1 plus 3x dx. Now, I'm going to share my screen and just show you a couple of the delta math ones. Just humor me for a second because they do this a little bit differently. It's not bad, it's just a little bit different. So when you go to this first section, oh, it looks like there's 1,000 sections, but there's only one problem in each one of those. The reason I did that is so you wouldn't do 4 right sums and 4 left sums. Like I made you do 1 right, 1 left, 1 trapezoid. Do you get what I'm saying? So it's going to look like a ton of things, but there's only one problem in each of them. So don't freak out. So these, instead of, do you see how there's not a limit? Instead of having it be infinite, they give you a number of subintervals. They're going to literally tell you, do you see how it's 20 right there? Okay. Pay attention because this is the first thing you're going to do. So the 20 goes there. They tell you that number. Okay. Now, where does this start? 2. So you're going to have 2 plus. Now, because they didn't make it infinite, there's no n. All right. You're going to take the 20 and divide it by the length of this. So from 2 to 6 is how far? 4. So 20 divided by 4 is 5. So it's k over 5. And then in the other one, you put a 1/5. It would be n over 5. They just don't do the n. They just took the n out of it. Do you get what I'm saying? Okay, but it's the same thing. You just take the number, put it there. It's just instead of infinity, it's 20. 20 divided by 4 is 5. Like, do you get what I'm saying? Okay, try, and then it's going to tell you your summation is correct. Plus submit. Okay, and then here's how these look. These are kind of cool. We want to go from 1 to 7 with 6 subintervals. So that means each one would be 1, go. It draws them for you, which is sweet. It says right sum. Do you see that? Right sum. So I'm going to pull these up until the right side attaches to the graph. Do you see how I'm making the right side attach? This is so cool. Like, it's so visual. I know, this is just visually pleasing to me. It's very concrete, like you can see it, right? So is this over or under? Yeah, it was over because the graph is increasing.